In this video, we'll talk about the concept of a relation and a function. And just think about this. When you hear the word relation, what comes to mind? I think about perhaps a relationship between two people, right? A mother and daughter, father, son, husband, wife. I think about maybe a relationship between how much time I spend studying and the score I make on a test, or how many minutes I exercise and the number of calories that I burn. So when there is a correspondence between two sets of information, we compare a piece of information from one set with a piece of information from the other set to form a set of ordered pairs. And this set of ordered pairs that we denote with x, y is called a relation. The x value is the input value or the independent variable. The set of x values is called the domain of the relation. The y value is the output value or the dependent variable. Right, the value of y depends on the value of x. And the set of y values is called the range of the relation. A relation can be represented in several different ways. We can represent it numerically by just giving a set of ordered pairs that can be given in literally a set or a table. We can represent a relation algebraically by some equation, graphically by a graph, or we can verbally describe the relationship. But understand we're looking at two sets of information that we're pairing together in some way, and the set of ordered pairs that are formed from that relationship are called the relation. So we're going to look at an example, and we are going to be given a set of ordered pairs. If we're not, we're going to write the set of ordered pairs that result from the relation that's given, and we will then identify the domain and range of each relation. In the first example, we have a relation is defined by the set of ordered pairs, -3, 4, -1, 2, 0, 4, 2, 7, and 5, 1. So the relation is given by this set of ordered pairs. We want to identify the domain of the relation. So the domain of the relation is the set of x values. So if I look at the x values, I have -3, -1, 0, 2, and 5. So the relation has these x values that I just pull out to have my domain, and I would typically write these in order from smallest to largest. So I would write in the set notation -3, -1, 0, 2, and 5. And then the range of the relation is the set of y values. So I have 4, 2, 4, 7, 1. So I want to write these in a set from smallest to largest. So what is that? 1, 2, 4 is listed twice, but we only need to put it one time, and then 7. In part B, we have the set of ordered pairs that corresponds to the relation is given by this graph. And so we want to first write the set of ordered pairs. Now on the graph we have, let's see, 1, 2, 3, 4, 5, 6 points. And those points are -4, 0, -2, 4, 0, 2, 1, -1, 9 halves, -10 thirds, and 5, 2. So I just take those points off the graph and put in the set notation, and that set is now my relation. Remember that a relation is a set of ordered pairs. The domain of that relation is the set of x values from all of those ordered pairs. So the domain from left to right, or from smallest to largest, is -4, -2, 0, 1, 9/2, and then 5. Okay, so the domain is a set of the x values from those ordered pairs. The range is a set of y values from those ordered pairs. So the set of y values, it's easier to read from the graph going bottom up because we know the smallest to the largest goes from the bottom to the top. So the smallest value would be -10/3, then -1, 0, 2, and 4. Now, a function is a special type of relation. So remember, a relation is just a set of ordered pairs. Really, there just has to be a correspondence between the x and y values. But a function is a special type of relation. And when I hear the word function, I think of something that works. Like if I go to a vending machine and I want to press a button to get my favorite candy bar, Mr. Goodbar, if I press that button, out comes the Mr. Goodbar, right? I should be able to press that button, and then the output, I would get the single Mr. Goodbar. For this vending machine to work, when I press a button, I should get one output, right? One candy. And that's the same thing for a function. A function is just a relation in which each x value corresponds to exactly one y value. That is, each input corresponds to only one output. What we'll do now is look at a relation and determine if it is a function. That is y a function of x? So if y is a function of x, for every input of x, I should have only one output value. So I have this relation given, and I want to state the domain and range of it, and then I want to determine if the relation is a function. The set of ordered pairs that I'm given is -3, 5, -1, 5, 0, 5, 2, 5, and 5, 5. So we'll start by talking about what is the domain of this relation. The domain, remember, is just a set of x values from those ordered pairs, from smallest to largest. So we have from -3, -1, 0, 2, and 5. And then the range is the set of y values. But notice that each y value of those ordered pairs is just 5. So my range consists of simply 5. And so, is this relation a function? That is, I'm asking myself, how many output values correspond to each input value? So each input value corresponds to how many output values? If this is only 1, then this is a function. So notice that -3 corresponds to only one number. It only corresponds to 5. -3 is nowhere else in my list, so there's only one output value for -3. -1 only corresponds to one value. 0 only corresponds to one value. 2 only corresponds to one value, and 5 only corresponds to one value. You can also see it if I list them in two columns, list all of the x values in a vertical column, so -3, -1, 0, 2, and 5, and list all of the y values in a second column, and we only have the number 5, and then draw a line to represent the correspondence. So -3 corresponds to 5, 1 corresponds to 5, 0 corresponds to 5, 2 corresponds to 5, and 5 corresponds to 5. But notice I only have one line drawn from each of these input values, so they only have one output value. So because every input value has only one output value, this relation is a function. Now in real life, what would this kind of look like? This would be a vending machine where I have, 1, 2, 3, 4, 5 different ways to get the same candy bar, right? So I input it, I press the number, but I'm only getting one thing. I just happen to have multiple ways to get that one thing. So there's no rule about saying that the output values can't be the same. I just want to make sure that my input has only one output. Now let's look at this relation. I have the set of ordered pairs -3, -1, -3, 2, -3, 5, -3, 6. So let's look at the domain and range. The domain is the set of x values. But notice that every x value in this set is -3. So my domain is just simply the set containing -3. My range is a set of y values, -1, 2, 5, and 6. So is this a function? I'm asking myself, how many output values does each input value correspond to? Well, -3, in fact, is my only input value, right? It's repeated in each of these ordered pairs. So -3 actually corresponds to 4 different output values, which contradicts the definition of a function. So this relation is not a function. And again, I can see this visually if I put these values in 2 columns. So the domain of -3 is in one column. And then to the right, I'm going to put a column of all my y values, -1, 2, 5, and 6. And I'm going to draw a line between every correspondence. So -3 corresponds to -1, -3 corresponds to 2, -3 corresponds to 5, -3 corresponds to 6. And so I can see that this input value corresponds to more than one output value, so it is not a function. In real life, think about this if this happened, that if you go to the college and you give them your Panther ID number and another student's name comes up, that would be a mistake, and it would be an issue if that Panther ID was assigned to multiple names. It would not be a functioning way to operate, and so this contradicts the definition of a function. Now we are given a relation defined by an algebraic equation, and we want to determine if y is a function of x. So we'll talk about the domain and range of these later, but we have the equation y is equal to -3x plus 1. So what we're asking ourselves is, if we input a value for x, how many output values correspond to that? So if I think about making a chart of values where we graphed, in fact we did this in an earlier section, if I input values like -2, -1, 0, 1, 2, and plug into this equation, y is found by just multiplying the input by -3 and then adding 1 to it. So like -3 times -2 plus 1 is 6 plus 1 or 7. -3 times -1 plus 1 is 3 plus 1 or 4. -3 times 0 plus 1 is just 1. -3 times 1 plus 1 is -2. And -3 times 2 plus 1, what is that? -6 plus 1 or -5. So notice that it doesn't matter what value I plug in for x, I get only one output value. So this is a function. In this next example, I want to determine if x equals y squared defines y as a function of x. So if we think about making a chart of values, this time we're saying that x is the square of y. So if we put in some values for y, we can square them and get what x is. So let's say we'll put in -2, -1, 0, 1, and 2. And when we square those values, we get what x is. So if we square -2, we get 4. If we square -1, we get 1. Square 0, 0. Square 1 is 1, and square 2 is 4. So we have these ordered pairs, 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. And so here we have an x value of 4 that corresponds to both -2 and 2. And so since we have an input value that corresponds to two different y values, this is not a function. Now we'll talk about how we can determine if a graph represents a function, and we do that with what's called a vertical line test. And if we have a vertical line passing through more than one point on a graph of a relation, then it is not a function. On the screen I have two examples of graphs. One is a parabola that opens to the right from the point -4, 0, and it goes through 0, 2, and 0, -2. And let's just think about that one for instance. So this is a graph that's opening to the right. When I draw a vertical line through it, I'm going to hit 2 points of the graph. And notice that along this vertical line, all of the x values are the same. In fact, I have a vertical line drawn through x is equal to 3. So there's 2 points on the graph that have an x value of 3. I don't know precisely what they were, or of course I chose one that doesn't go through an integer value. It looks something like, let's just say 2.8 and -2.8. But this vertical line going through 2 points shows me that there's an x value that has more than one output value, right? An input value with more than one output value, which contradicts the definition of a function. So this vertical line going through more than one point tells me that this graph of the relation is not a function. Now I have another example that is, we'll talk about these later, is actually a graph of a polynomial function. It starts in the third quadrant, goes up through -1, 0, goes up a little bit, then through the origin, and then back down, and then up through 1, 0, and then continues up. So when I draw a vertical line through any point on this graph, it only hits one point of the graph. And so since each vertical line hits only one point on the graph, it is a function because that's showing me that each x value corresponds to only one y value. So this would be a function. So let's look at this example. We have to use a vertical line test to determine if the relation defines y as a function of x. And we have the graph of a circle given. So when I'm thinking about, does this circle represent a function? Well, I can draw a vertical line through the circle. And when I draw it through the circle, notice that I'm going to hit 2 points of the graph. And so this vertical line touching more than one point tells me that this graph is not a function.